Welcome everyone. Myself, Professor Himanshu Thaplial. I will be giving my talk on a novel low power and energy efficient adiabatic logic in memory architecture using CMOS MTJ. This work has been performed in collaboration with my former PhD student, Dr. S. Dinesh Kumar. So let me define that whenever I refer MTJ, I mean to say the magnetic tunnel junction. So MTJ CMOS based logic in memory circuits have nearly zero leakage power. They are non-volatile and they have the high integration density. However, this MTJ CMOS based limb circuits suffer from the dynamic power dissipation. So in this research, we propose on novel solutions based on adiabatic logic to reduce the dynamic power dissipation of this logic in memory circuits, and we call this architecture as ALIM. ALIM refers for adiabatic logic in memory architecture. So just to give you the brief background on adiabatic logic, so as can be seen in this figure, in adiabatic circuits, you have this instead of the constant VDD, you have this represented by the power clock. So this power clock, this has been represented by a 4-phase power clock. So you can see that when the clock rises, you can, this is being represented by this figure here. So the energy is being supplied to your output nodes, and so the energy is coming to your output nodes, and depending on the function f and f bar gets evaluated based on the inputs. And then what we happen is that once the clock is, if you see, after some time the clock is starts falling down, this is being represented being in this carton here. So this energy is again recovered back to your original clock source, right? So that's why these adiabatic circuits are low power. However, as you can see that in this case adiabatic circuits are operating on this power clocks. So there is a time it takes for this output to go from the 0 to VDD. That is being represented here. So accordingly, you can think in this case, the power dissipation in adiabatic circuit is given by EC RC by T CVD square, where T is in the denominator. So in order to develop these adiabatic circuits as a low power circuit, the T should be very, very greater than RC. And that's why these adiabatic circuits, even though are very energy efficient, usually operates at low operating frequency. So this is an example of the magnetic tunnel junction. So MTJ consists of two ferromagnetic layers. One of them is a free layer, another of them is a fixed layer, and in between there is a sandwich layer that is represented by the oxide layer. So what you can think in this case, so there are two types of states are possible. One of them is the parallel state, that is the low resistance state, that is represented by the logic 1, or you can have the anti-parallel state that is represented by the high resistance state that is represented by the logic 0. So now this is an illustrative example of the conventional CMOS based MTJ logic in memory architecture. So you can see that the block consists of PCSA, that is a pre-charge sense amplifier. Then this is being represented here. This is a PCSA circuit. Then you have the dual rail CMOS that is being represented here. That is the volatile logic. And then you have this non-volatile component, that is the MTJ, that is the non-volatile component of your circuit, right? So so this how this conventional circuit works: when the clock is 0, that is the pre-charge phase. So your output nodes in this case are charged to your VDD. Then during the evaluate phase, when the clock is 1, you can think in this case the output get discharged based on the resistance path provided by this MTJ and MTJ2, and also based on the input conditions. So finally, you will have one of the output to the VDD, and another output will be the complementary in the ground state. That's how it works. Now, now what we did in this case, that if you see the conventional PCSA, it consists of some clock circuits, and however, if you remember, adiabatic circuit also have some clocks. So we came out with a modified design, and we call that as a adiabatic logic in memory architecture. Here we have a novel type of a PCSA design. So so our design uses clock for two purposes: one for pre-charging the output, and second, we also use for recycling the charge from the output nodes. And moreover, as you can see, since we are using this PCSA to perform both functions, you will see that our PCSA is designed such that it takes less transistor than the conventional PCSA. This is an illustrative example of a proposed ALIM XOR gate where MP1 and MP2 transistors are used for pre-charge the output. And this M1 is the discharge is the discharge transistor which help us to stabilize the output. So this logic works in this clock work in four phases that is being represented here. That is like a T1, T2, T3, and T4, right? And now another interesting thing in this case, so we assume that all the transistor except these discharge transistors are of equal size. We size this discharge transistor comparatively bigger than the other transistors because we want to make sure that our outputs are reset before the evaluation of the next clock cycle. So this is an illustrative example. Here you can see that assuming this is the T1 phase, it is also called as the wait phase that is being represented here. So here you see that this M1 transistor is on, and we are assuming that one of the resistance path, in this case, we are assuming that resistance of RMTJ1 is greater than the resistance of RMTJ2. So what is happening in this case that after some time, you can think in this case when your clock started rising, right? So this discharge signal has been again in the ground state now. So what will happen that your output nodes will start charging both of them XOR and XNOR, since one of them has one of them, depending on the low resistance path, in this case XOR, will completely discharge to the ground. However, this XNOR node will finally charge to the VDD, and this XOR will be at the ground state. Okay. Now after some time, you can think in this case this T3 is more like a hold phase, so it will just maintain the state. Finally, during the recovery phase, the clock start falling down, and what will happen during this phase that it will provide the energy recovery will happen through these transistors, and so from the XNOR node, the energy will start recovering again to the clock source, and it will stop at the point of the VTP. So because at that point you can see this MP2 will also turn off. Now what will happen that during the next T wave 5, we will again, if you see at the time this discharge signal is on, and so during this time this will be more like the state like this. So what will happen that whatever the VTP charge that is stored at this XNOR node will be charge shared between this XOR and the XNOR, and this we will show you in one of the slides in the upcoming slides. So this is how you can design a ALIM based magnetic full adder. So this portions represent your sum block, and this portion represent your COT block. And these are some of the logic equation that we have used to implement these circuits. Now this is the MTJ device parameters which we have used for simulation. Okay. And next thing we want to discuss is that the waveforms. So here you can see this shows the correct functionality of the ALIM based magnetic full adder. Moreover, you can see that as I discussed with you that when the discharge signal is on, you may notice this charge sharing, right? These are the places where you will see the charge sharing. So the charge sharing do occurs, and moreover, as I told you, is that uh, moreover, since the energy is recovered, our circuit is very low power compared to the conventional PCSA. This is some example that has been shown here. Here you can see the energy consumption in the femtojoules, and this is the time period. So over a time period, you can say that our ALIM based adder is comparatively has low energy consumption compared to the PCSA adder. Now these are some of the numbers. So you can think in this case that uh, our design has this XOR gate has also low energy, and this XOR gate has also low power. Moreover, it takes the less number of these MOS transistors And I just told you why it takes the less number of MOS transistors, because we are saving the transistor in the PCSA design. Similarly, this is the reason for this magnetic full adder. Again, here it is 26 MOS, but in our case where it's 18 MOS, because again we are saving the number of transistors in the PCSA design, and also we are having the low power and the low energy and the low power characteristics. So this is an illustrative example here where we have scaled down the supply voltages, and as can you see from here, even when you scale down your supply voltages, you can see that our circuit is still work reliably here. Moreover, you can think in this case is our ALIM architecture is again low power as well as energy efficient compared to the PCSA adder design. Now, in summary, what we can understood is that we propose a novel adiabatic logic in memory architecture. The architecture can be generalized for any logic circuit design. However, in this case, we have shown the illustrative example with the case of XOR and a magnetic full adder. We have illustrated that this ALIM-based architecture has significant energy and the power saving compared to the existing pre-charge sense amplifier based magnetic full adder. Moreover, uh, why we are having the low power characteristic, because you can think in this case by we are using the this energy recovery property of adiabatic computing. Moreover, since we are able to utilize the commonality of the clock in adiabatic circuit and MTJ CMOS circuits, our circuit has also the less number of transistors. So these types of designs can be used for the low power low energy applications. For future work, we plan to develop some more complex circuits, such as the mapping of these algorithms, complex algorithms on our ALIM design, and also designing some sort of complex circuit and on such as flip-flop, and moreover to perform more reliability analysis of the proposed ALIM circuits. So with that, I like to conclude my talk. Thank you very much.